galaxy isn't just drifting through space as a single isolated island of stars. It's surrounded by a swarm of much smaller companions. These tiny galaxies orbit us like moons, locked in a slow gravitational dance that has been going on for billions of years. They don't look impressive compared to giants like the Milky Way or Andromeda, but without them, the universe would be unrecognizable. Some of them are being pulled apart as we speak, leaving behind long rivers of stars across the sky. Others may be time capsules from the dawn of the cosmos, carrying within them the secrets of how the very first galaxies formed. To study them is to peel back the layers of our own galactic history and to glimpse the future of the Milky Way. Subscribe now to Stellify Science for mind-expanding journeys, because what comes next will change how you see everything. Prepare yourselves. We begin. What counts as a galaxy? Setting the boundaries. When we look at the night sky through a telescope, we see countless collections of stars. Some are vast, stretching across hundreds of thousands of light years, while others are far smaller and fainter. To the human eye, they can all look similar, points of light grouped together in the dark. But for astronomers, there's an important question hiding here. What counts as a galaxy? At first, it seems simple. A galaxy is a huge group of stars. But when you look closer, the line between a galaxy and a cluster of stars becomes much harder to draw. The deeper astronomers have peered into the cosmos, the more confusing this boundary has become. A galaxy is a system, a living environment of matter, gas, and invisible forces. For many scientists, one of the key traits that separates a galaxy from a simple cluster is gravity. In small clusters, the gravity binding the stars together comes only from the stars themselves. But in galaxies, there's an extra element: dark matter. This mysterious material makes up most of a galaxy's mass and acts as a kind of invisible glue. Dark matter forms a halo around the galaxy, giving it the strength to pull in gas, shape the orbits of stars, and even resist the pull of nearby galaxies. If you strip away this unseen halo, the structure quickly falls apart. For this reason, many astronomers argue that a true galaxy must show signs of being supported by dark matter. Larger galaxies often pull on their smaller neighbors, tugging at them with powerful tidal forces. These forces can stretch and twist a smaller object until it breaks apart completely. Star clusters caught in the orbit of a giant galaxy are often shredded over time, their stars scattered across the sky. But dwarf galaxies, even tiny ones, often remain intact for billions of years. Their dark matter halos protect them, helping them hold together despite the immense gravitational tides. This endurance is one of the reasons astronomers treat them as real galaxies rather than clusters. But not every system fits neatly into this rule. Some of the faintest galaxies ever discovered seem to blur the boundary. Ultra-faint dwarf galaxies, for instance, contain only a few thousand stars, less than some star clusters. Yet they behave differently. They spread their stars over a wider area and move in ways that suggest the presence of far more mass than we can see. The only explanation is that they're dominated by dark matter. In this way, galaxies that look small and fragile can still count as galaxies because their invisible scaffolding is so strong. The ability to create new stars. Another trait that often separates galaxies from star clusters is the ability to create new stars. In many galaxies, clouds of gas collapse to form new generations of stars, a cycle that can continue for billions of years. Star clusters, on the other hand, are usually born in a single burst. After their first round of stars ignite, they quickly burn through their gas. With no fuel left, they cannot make new stars. This difference in star formation history is crucial. It makes galaxies evolving ecosystems, while clusters are more like fossils of a single event. If you look at the chemical makeup of stars, this contrast becomes even clearer. Galaxies show a wide variety of chemical fingerprints because new stars form from gas, enriched by older ones. Clusters, by comparison, show a much simpler record, locked in at birth. Still, even here, the edges blur. Some large star clusters, like Omega Centauri in the Milky Way, show signs of chemical complexity that resemble galaxies. In fact, some scientists think Omega Centauri might actually be the remnant of a dwarf galaxy stripped of most of its stars and gas long ago. This possibility shows just how tricky the boundary is. Objects can change over time, moving from one category to another. A galaxy torn apart by tidal forces can leave behind a star cluster. A cluster that holds more mass than expected might secretly be the leftover core of a destroyed galaxy. The way stars move within a system tells you about the gravity holding it together. In clusters, the motions of stars can be explained by the visible mass alone, but in galaxies, the stars move too quickly for the visible matter to keep them bound. Something else, dark matter, must be there, tipping the balance. By studying these motions, astronomers can decide if a faint object in the sky is truly a galaxy or just a cluster. Even with all these criteria, there are still debates. Some astronomers argue that insisting on dark matter as a requirement is too restrictive, because in certain cases, galaxies can lose much of their dark matter through interactions. Others suggest that star formation isn't the best marker, since even galaxies can run out of gas and stop making new stars. What remains constant, though, is the idea of complexity. A galaxy isn't just a group of stars stuck together. It's a system shaped by both visible and invisible matter, built to last and capable of evolving across cosmic time. If we draw the line too narrowly, we risk overlooking small but important systems that may hold clues to how galaxies first formed. If we draw it too widely, we risk blurring the unique processes that make galaxies different from clusters. The faintest galaxies ever found, barely visible against the dark, push the definition to its limits. Are these ghostly systems truly galaxies, or are they something in between? The answer is still unfolding. This uncertainty reflects a larger truth about science. The universe doesn't always fit neatly into the boxes we create. Our definitions are tools meant to help us understand, but the cosmos constantly challenges them. In the case of galaxies, the challenge is particularly sharp because these systems are central to the structure of the universe. They're the homes of stars, planets, and perhaps life itself. Understanding where galaxies begin and end helps us understand how the universe itself is organized. The realm of the small, dwarf galaxies. Explained. If the great spirals and giant ellipticals are the lords of the cosmic stage, dwarf galaxies are their quiet companions. They may not dazzle the eye with sweeping arms or brilliant cores, but they are everywhere. In fact, when astronomers count the number of galaxies in the universe, the majority are dwarfs. These are the lightweights of the galactic family, small and faint, sometimes so faint they're almost invisible against the dark. Our galaxy contains around 200 to 400 billion stars, depending on how you count them. A dwarf galaxy, in contrast, may have only a few billion stars, or even fewer. Some of the tiniest examples contain just a few thousand stars. To put that in perspective, a large star cluster inside the Milky Way can contain hundreds of thousands of stars. A typical dwarf might span a few thousand light years compared to the Milky Way's 100,000. Some are so compact they would fit comfortably inside a single spiral arm of a large galaxy. Others are puffed up and spread out, their stars scattered thinly across space. Despite these differences, one thing unites them. Dwarfs lack the grandeur of large, well-structured systems. They don't have the neatly wound spiral arms we see in galaxies like Andromeda, nor the smooth, glowing balls of stars seen in giant ellipticals. Instead, they often appear irregular, lopsided, and messy. Their stars are unevenly distributed, their gas clouds ragged, as if they were never finished being built. This irregular look is partly the result of their weakness. Because dwarf galaxies have less mass, their gravity isn't as strong. That means they have a harder time holding onto their stars, gas, and dust. A close encounter with a larger galaxy can distort them, leaving behind a warped shape. Many dwarfs are satellites of bigger galaxies, and their appearance shows the scars of these interactions. Ancient building blocks. Even so, dwarf galaxies aren't just leftovers or scraps. They're thought to be some of the first building blocks of the universe. In the early cosmos, before giant galaxies formed, small clumps of gas and dark matter gathered into dwarfs. Over time, many of these merged together to form larger galaxies. In this way, the great spirals and ellipticals we see today are the product of countless smaller systems, combining over billions of years. Some dwarfs survived this violent process intact, orbiting as satellites around their bigger cousins. These survivors may carry valuable clues about what galaxies were like in the earliest times. Not all dwarfs look the same. Astronomers divide them into categories based on their shape and behavior. Some dwarfs, called dwarf spheroidals, are diffuse and faint, often containing very few stars spread across a large volume. They show almost no gas and little to no star formation, making them ghostly, dim objects. Others, called dwarf irregulars, are more active. These are clumpy, gas-rich systems where new stars still form. In fact, dwarf irregulars can shine brightly in certain regions, with glowing clouds of hot gas lit up by clusters of young stars. There are also dwarf ellipticals, which are smoother and rounder than irregulars, but smaller than the giant ellipticals seen elsewhere. Chemical simplicity. Compared to large galaxies, dwarfs tend to be poor in heavy elements. Stars create heavy elements through nuclear fusion and supernova explosions. But in dwarfs, many of these enriched materials escape. With weak gravity, they can't hold on to the blast of a supernova as easily as large galaxies can. Over time, this means their gas remains relatively primitive, more like the early universe. Astronomers can thus study conditions similar to those that existed long ago, before galaxies like the Milky Way were fully developed. Dark matter dominance. Despite their low star counts, dwarf galaxies seem to be dominated by dark matter. In fact, pound for pound, they often contain more dark matter relative to visible matter than the giants do. This is why they can survive at all, even when they're so faint. Studying these halos help scientists learn about the nature of dark matter itself. Some of the smallest known dwarfs have been called dark matter laboratories because of how sensitive they are to its invisible presence. The Milky Way is surrounded by dozens of dwarf galaxies. The most famous are the Large and Small Magellanic Clouds, visible to the naked eye in the southern hemisphere. These two irregular dwarfs are gas-rich, full of young stars, and currently interacting with both each other and the Milky Way. Their distorted shapes and star-forming regions are evidence of this gravitational dance. Closer in, Our galaxy also hosts a population of tiny spheroidal dwarfs, some of which were only discovered in recent years through careful surveys of the sky. These faint companions are so diffuse that they almost vanish into the background. Yet they're still galaxies in their own right. Other, large galaxies also have retinues of dwarfs. Andromeda, for example, is accompanied by more than 30 known dwarf galaxies, forming a miniature system of its own. In fact, dwarf galaxies are so common that astronomers believe there may be far more waiting to be discovered, especially in regions of the sky that are harder to observe. Many of them could be hiding at the edge of detectability, faint clouds of stars that require the most powerful telescopes to spot. Though they're small, dwarf galaxies can still make a big impact. When a large galaxy absorbs a dwarf, it can stir up star formation, add fresh gas, and alter the larger system's structure. Our own Milky Way shows signs of having merged with dwarfs in the past, leaving behind trails of stars in its halo. Some of the globular clusters in our galaxy may even be the remnants of ancient dwarfs stripped down to their cores. In this sense, dwarfs are both the seeds of galaxies and the fuel that continues to shape them. The missing satellites problem. There's also a mystery tied to dwarf galaxies known as the missing satellites problem. According to computer simulations of dark matter, galaxies like the Milky Way should be surrounded by hundreds, maybe thousands, of small dwarf companions. Yet when astronomers look, they find far fewer. Either we're not seeing the faintest ones, or something about the way galaxies form is different from what the models predict. This puzzle remains unsolved, but every new dwarf discovered brings us closer to an answer: the hidden majority of galaxies in the universe. They shine like lighthouses in the dark, while the dwarfs are more like faint sparks scattered everywhere. Their small size and low brightness make them nearly invisible in wide surveys of the sky. To detect them requires deep, careful searches, and often even then they remain little more than faint smudges against the blackness. Astronomers have learned to look for these hidden galaxies in clever ways. One approach is to search near larger galaxies, where dwarfs often cluster as companions around our own Milky Way. The Large and Small Magellanic Clouds are the easiest to see, but fainter satellites like the Draco Dwarf or the Ursa Minor Dwarf are so dim that they're only visible through detailed surveys of star motions and brightness. As telescopes have improved, more of these faint companions have been discovered, and each new find suggests that there are many more waiting to be revealed. Modern detection methods. Another method is to use wide-field digital surveys that map the sky in detail. In recent years, projects like the Sloan Digital Sky Survey, SDSS, have uncovered dozens of ultra-faint dwarfs by picking out subtle clumps of stars that move together. These discoveries have shown that the universe is teeming with small galaxies. And yet, astronomers are convinced that we've only found a fraction of them. When scientists run computer simulations of how galaxies form, they begin with the growth of dark matter halos. These halos form from the gravitational pull of dark matter, drawing in gas and creating the conditions for stars to form. In the models, small halos form first, then merge to create larger ones. This process naturally produces an enormous number of small galaxies, far outnumbering the giants. It's a bottom-up picture of cosmic growth, where the small arrive before the big. Evidence from our own local group supports this view. The local group, which includes the Milky Way, Andromeda, and a collection of smaller galaxies, is dominated by dwarfs. Beyond the two giant spirals, nearly every other member is a dwarf galaxy. Some are irregulars, while others are spheroids, barely visible, even with modern instruments. This small corner of the universe offers a snapshot of the broader truth. Wherever there are galaxies, dwarfs are the most numerous. A dwarf galaxy, with only a few million stars, produces far less light than a spiral with hundreds of billions. By the time that dim light has traveled across millions of light years, it becomes almost impossible to detect. Our telescopes must compete not only with distance, but also with the faint glow of background stars, cosmic dust, and even the light pollution of Earth itself. Many dwarfs blend into the cosmic background like shadows. Detecting them requires long exposures and sensitive instruments, and even then, astronomers may only identify them as small overdensities of stars, rather than clear, shining galaxies. If most galaxies are dwarfs, then they may hold most of the information about how galaxies form and evolve. Large galaxies like the Milky Way have undergone many mergers, collisions, and bursts of star formation that blur their history. Dwarfs, being smaller and simpler, often carry a more direct record of what happened billions of years ago. The universe is often described as a web, with galaxies strung along filaments of dark matter separated by vast voids. If dwarfs dominate the numbers, then these filaments are even richer than we once thought. Each faint dwarf adds weight to the cosmic scaffolding, helping us map the invisible skeleton of dark matter that holds everything together. Without accounting for them, our picture of the universe is incomplete. Looking ahead, astronomers expect the hidden majority to step into the light as new tools become available. Telescopes like the Vera C. Rubin Observatory, with its ability to survey wide areas of the sky in great depth, are expected to reveal hundreds of new dwarfs around the Milky Way and beyond. Space-based observatories freed from Earth's atmosphere will also peer deeper, detecting faint smudges of light that ground-based telescopes cannot. The missing satellites problem. In the late 20th century, astronomers began to run large computer simulations to understand how galaxies formed. These simulations used the known laws of physics and the idea that dark matter makes up most of the universe's mass. Out of this came a striking picture. Galaxies like the Milky Way should not be alone. They should be surrounded by hundreds, maybe even thousands of small dark matter halos, many of which ought to host dwarf galaxies. In other words, our galaxy should have a massive swarm of tiny companions like bees around a hive. But when astronomers looked into the sky, they saw something different. Instead of hundreds, only a few dozen satellite galaxies were known. This mismatch between prediction and observation became known as the missing satellites problem. The problem stands out because simulations reproduce large-scale cosmic structure with impressive accuracy. The cosmic web, the clustering of galaxies, the growth of large halos, all match what we see in the universe. But at small scales around galaxies like our own, the numbers don't add up. The dark matter, halos that should exist in great numbers seem to be empty. Either they exist, but don't host galaxies, or our understanding of dark matter itself is incomplete. Searching for solutions. At first, some astronomers wondered if the problem might be simple. Perhaps the missing satellites were there, but just too faint to detect. As digital surveys and deeper imaging came online, more faint dwarfs began to appear around the Milky Way. The Sloan Digital Sky Survey, for instance, uncovered many ultra-faint dwarfs in the northern sky. Later surveys, like the Dark Energy Survey, found more in the south. Each discovery chipped away at the missing satellites problem. Yet even today, the total number of known dwarfs around the Milky Way is in the dozens, far fewer than the hundreds predicted. If the satellites aren't simply hiding, another possibility is that the simulations assume too much about how gas and stars behave in small dark matter halos. In theory, Every halo should be able to collect gas and form stars, but in practice, many may fail. In the early universe, powerful radiation from the first stars and quasars may have blasted away gas from small halos before they could form galaxies. Later, supernova explosions inside early dwarfs could have blown out much of their remaining gas, shutting down star formation permanently. If this happened often enough, then many dark matter halos might be dark themselves, containing no stars at all, invisible to telescopes. In this view, the missing satellites aren't truly missing. They're there, but they never lit up. Alternative dark matter models. Another angle is that the physics of dark matter itself may not be what we think. The standard model of cosmology assumes that dark matter is cold, meaning it moves slowly compared to the speed of light and clumps together easily. Cold, dark matter predicts lots of small halos, just the kind that lead to the missing satellites problem. But what if dark matter behaves differently? If dark matter is warm, moving faster in the early universe, it would smooth out the smallest structures and prevent as many dwarfs from forming. If it can also interact with itself in subtle ways, it might further erase the smallest halos. These alternatives remain speculative, but the missing satellites problem is one of the strongest motivations to explore them. The Milky Way's satellites aren't the only place to test the issue. In Andromeda 2, the numbers fall short of predictions, although it seems to have slightly more companions than the Milky Way. Looking at clusters of galaxies provides another test. In larger environments, small galaxies seem to be more abundant, but the smallest predicted dwarfs are still hard to find. Across all scales, the puzzle repeats itself. The missing satellites problem blends two different mysteries. On one hand, it might be about how galaxies form. Maybe star formation shuts down in small halos more often than we thought. On the other hand, it might be about dark matter itself. Maybe the invisible substance we rely on in our models has properties we haven't yet uncovered. The challenge is to separate these two. If we can detect more ultra-faint dwarfs, we might confirm that many small halos really do host galaxies. If we cannot, then we may need to rethink the very nature of dark matter. In recent years, progress has been made by carefully mapping the sky and looking for stellar streams. These streams show that some satellites have come and gone. This means that the Milky Way's current census of dwarfs isn't the whole story. Over billions of years, many more may have existed only to be absorbed or destroyed by the host galaxy. If so, then the simulations may not be entirely wrong. Still, even accounting for faintness and destruction, the gap between theory and observation remains wide. Some estimates suggest that the Milky Way should have at least a few hundred satellites. Unless our surveys are missing nearly all of them, we're left with a serious tension. This is why the missing satellites problem is often described as a test of the standard model of cosmology. If our picture of the universe is correct, then the missing satellites must be out there. The missing satellites problem forces astronomers to test the limits of their models and to look more carefully at the smallest scales of the universe. Whether the answer lies in faint galaxies we haven't yet seen, in physics we don't yet understand, or in a mix of both, the puzzle helps drive research forward. How dwarf galaxies are discovered. One of the earliest ways to find a dwarf galaxy was to stumble across it by accident. A careful astronomer, scanning photographic plates of the sky, might notice a faint smudge that didn't quite match the appearance of a known star cluster. These early discoveries were often uncertain because the difference between a loosely bound group of stars and a true galaxy is difficult to see at a glance. But as instruments improved and digital imaging replaced film, astronomers began to design surveys that specifically looked for such faint smudge-like objects. Wide-field surveys became an essential tool, allowing the entire sky to be mapped with enough detail to capture even the faintest structures. Digital sky surveys. The SDSS was one of the most important steps forward. Using a dedicated telescope in New Mexico, it scanned large parts of the sky with high precision and produced one of the most complete maps of stars and galaxies ever made. Within this vast dataset, researchers began to notice overdensities of stars, tiny patches where more stars appeared than expected. These overdensities often turned out to be dwarf galaxies. What was once overlooked in the night sky was suddenly visible thanks to the careful statistical analysis of enormous amounts of data. Star counts became one of the primary methods of dwarf galaxy discovery. Instead of looking for a glowing patch of light, astronomers would search for regions where stars seemed unusually concentrated. A dwarf galaxy might only reveal itself as a slight bump in the star count graph. But with enough data and careful analysis, these bumps are the fingerprints of hidden companions. This method is particularly powerful near the Milky Way. Our galaxy contains billions of stars, which makes the background sky crowded and noisy. But when a dwarf galaxy is present, the stars in that patch of sky often share similar properties, such as color or brightness. By filtering for stars that appear older, redder, or dimmer, characteristics typical of dwarf galaxy populations, astronomers can pull a faint galaxy out of the overwhelming glare of the Milky Way. Ultra-faint discoveries. Ultra-faint dwarfs, discovered in the past 2 decades, contain so few stars that they are on the edge of what we might consider a galaxy at all. Detecting such objects requires not just powerful telescopes, but clever techniques to filter signal from noise. The faintness of these dwarfs means that if you were standing inside one, you might not even realize you were in a galaxy at all. The stars would be too sparse. The night sky not much different from what you would see on Earth. To uncover such fragile systems, astronomers now rely on deep surveys that go far beyond the sensitivity of earlier projects. The Dark Energy Survey, carried out using a 4-meter telescope in Chile, has been one of the most successful at finding new dwarf galaxies. By imaging large areas of the southern sky to extreme depths, it revealed dozens of ultra-faint dwarfs orbiting the Milky Way. Modern instruments also make use of motion to confirm discoveries. A random patch of stars could be mistaken for a dwarf, but true galaxies have stars that move together, bound by a shared gravitational field. By measuring the tiny shifts in starlight caused by motion, something that requires highly sensitive spectrographs, astronomers can test whether a faint group of stars is truly a galaxy. If the stars show random, unconnected motions, the group might be a cluster. But if they move in a way that suggests they're bound together by invisible mass, then the presence of dark matter reveals it to be a galaxy. The Hubble Space Telescope has been used to resolve individual stars in suspected dwarfs, allowing astronomers to measure their ages and confirm their nature. With its sharp vision above Earth's atmosphere, Hubble can distinguish details that ground-based telescopes often blur together. Future telescopes promise to revolutionize the search further. The Legacy Survey of Space and Time will repeatedly scan the sky, providing a dynamic map that can reveal not only faint galaxies, but also how they change over time. The process of discovery is slow, patient, and ongoing. But with every faint smudge revealed, the hidden structure of the cosmos becomes a little clearer. Mapping the Milky Way's neighborhood. Around the Milky Way swarm dozens of smaller companions. These satellites vary enormously in appearance, structure, and size. Yet together, they paint a picture of how diverse the galactic family truly is. The most obvious members of this family are the Magellanic Clouds. The Large Magellanic Cloud, LMC, is bright enough to be seen with the naked eye from the southern hemisphere. With roughly 30 billion stars, it's by far the largest of the Milky Way's companions. Its smaller sibling, the Small Magellanic Cloud, contains only a few billion stars, but still easily outshines nearly all the other dwarfs in our neighborhood. Both are irregular galaxies, lacking the clear spirals or smooth ellipses of giants like the Milky Way. They're filled with gas, actively forming new stars and display regions of glowing nebulae where stellar nurseries flourish. These two galaxies are the heavyweights of the Milky Way's entourage, and their mutual interaction with each other and with the larger galaxy makes them among the most studied objects in the sky. The dwarf spheroidals beyond them lies a retinue of smaller, more fragile systems. These are the dwarf spheroidals, so faint that they remained hidden until quite recently. They're ghost-like, often containing only a few 100,000 stars spread over large volumes. Unlike the Magellanic Clouds, they hold little or no gas, and new star formation is absent. Examples include the Sculptor, Fornax, and Carina dwarfs, each one a dim collection of ancient stars orbiting tens to hundreds of thousands of light years away. Still closer to the Milky Way, some satellites creep almost unnoticed through its halo. The Sagittarius dwarf, discovered only in the 1990s, is being torn apart as it plunges through the disk of our galaxy. Long stellar streams arc across the sky, marking its remains as it's steadily digested. The Canis Major dwarf, another low-mass companion, is similarly in the process of dissolution, its stars smeared into arcs that wrap around the Milky Way's outskirts. These galaxies are reminders that the boundaries of a galaxy are porous. Extended census. The census of satellites extends even farther, stretching hundreds of, thousands of light years from the Milky Way's center. Some companions like Leo 1 and Leo 2 orbit at great distances, almost on the edge of the galaxy's sphere of influence. Despite their remoteness, they still remain tied to the Milky Way's gravity, tracing slow orbits over billions of years. Each of these systems adds a different chapter to the galactic family history, some showing evidence of ancient bursts of star formation, others displaying a smooth population of only old stars. The satellites can be grouped not just by their brightness or size, but also by their type. The gas-rich irregulars, like the Magellanic Clouds, are rare but spectacular. The gas-poor spheroidals are numerous, faint, and widely dispersed. Ultra-faint dwarfs push the definition of a galaxy to its edge. Together, they outline a spectrum of companions. Another important way to look at the neighborhood is by distance. A few dwarfs lie very close, only tens of thousands of light years from the Milky Way's center, deep inside the halo. Others drift far beyond at distances closer to 1,000,000 light years, where the pull of the Milky Way competes with that of Andromeda. The distribution isn't even. Clumps of satellites appear in certain regions, possibly tracing the remnants of larger systems that broke apart long ago. Some researchers even argue that the satellites may be arranged in vast plains or streams, although whether this is real or just an illusion is still debated. The Magellanic Clouds are giants with billions of stars each. The classic spheroidals contain millions of stars. The ultrafaints may have only hundreds or thousands. Yet across this wide range, all are considered galaxies. By charting the Milky Way's neighborhood in this way, astronomers build a picture of not just what exists today, but also of the history of interactions. The bright irregulars may represent fresh arrivals, not yet stripped of their gas. The faint spheroidals may be the remains of systems long battered by the Milky Way's tides. Some of the ultra-faints may be fossils of the very first galaxies that formed in the universe, preserved in miniature form. Each companion offers a clue to how galaxies grow. Stellar streams, the ghostly trails of consumed galaxies. If one could strip away the glare of the Milky Way's disk and look only at the halo, the sight would not be smooth or empty. Instead, it would resemble a spider's web woven from stars, thin and delicate, but stretching over immense distances. These are stellar streams. They're not whole systems anymore. They're the shredded remains, their stars pulled free and stretched into long arcs. The Milky Way's halo is filled with them, like a cosmic graveyard of companions that could not resist the pull of the giant at the center. The making of streams. Imagine a small galaxy falling into the Milky Way. Its stars move together, bound by their mutual gravity. But as it circles the larger galaxy, the tidal pull begins to stretch it. Stars on the far side feel a slightly weaker tug, while those on the near side feel a stronger one. Over time, the system unravels, its stars peeling off and forming tails. These tails follow the original orbit, wrapping around the galaxy in long trails that can span hundreds of thousands of light years. What was once a single coherent body becomes a dispersed ribbon, impossible to separate from the greater halo except by careful observation. One of the most famous of these is the Sagittarius stream, the debris of the Sagittarius dwarf galaxy. Its stars form arcs that wrap almost entirely around the Milky Way. Other streams, like GD1, Orphan, and Palomar 5, are equally striking, though often fainter. Some are linked to disrupted dwarf galaxies, others to globular clusters that were pulled apart. Each one is a fossil record, written in the positions and motions of stars. By studying them, scientists can retrace the orbits of vanished systems and reconstruct the history of the Milky Way's growth. Detection challenges. Detecting them is a challenge. Many are faint, lost in the sea of background stars. But surveys that map the sky in detail have revealed more and more of them. What once seemed invisible became patterns that could be traced and measured as they orbit the Milky Way. They're shaped not just by visible matter. If the dark matter halo were smooth, the streams would be graceful and unbroken. But some appear clumpy, torn in places where the stars have been deflected. These disruptions may reveal the presence of invisible dark matter clumps, remnants of smaller halos that never formed into galaxies. In this way, stellar streams act like detectors, mapping the unseen structure of the galaxy's dark matter through their distortions. Even after a dwarf galaxy is completely consumed, its stars don't vanish. They continue to move together, sometimes for billions of years. Over time, the stream thins and disperses, blending into the halo until it can no longer be distinguished. But before that final dissolution, it offers a glimpse into a violent past. Some astronomers describe the Milky Way's halo as an archive, with stellar streams as the documents within it. Taken together, they show that the Milky Way grew layer by layer. Without streams, this history might be hidden. Notable examples. The Orphan stream is one example of a particularly evocative case. As its name suggests, the parent system that created it has been almost entirely destroyed, leaving behind only the ribbon of stars. Astronomers can measure the motions of these stars and deduce the orbit of the lost system. But the original dwarf is no longer identifiable. It has been erased, leaving only its trail. Palomar 5, on the other hand, still has a surviving core, a globular cluster that continues to shed stars into a long pair of tidal tails. Observations show that it's slowly dissolving, and in time, it too will vanish, leaving only its stream as a memory. Some streams are twisted and unfolded, reflecting complex histories. A system might orbit many times, each pass stretching new stars into the halo. Overlapping arcs can make the structure seem chaotic, but careful study reveals the rhythm of repeated disruption. These patterns not only map past interactions, but also allow astronomers to test models of the Milky Way's formation. In a sense, stellar streams are evidence of continuity. The dwarf galaxies and clusters that birthed them no longer exist in their original forms, yet their stars live on, circling the galaxy as part of a new whole. The Milky Way's brightness, its richness, is due in part to these absorbed companions. Without them, it would be smaller, less grand. The Large Magellanic Cloud, a satellite rivaling a galaxy, with its broad spread of stars, active regions of star formation, and noticeable spiral-like features. The LMC looks more like a scaled-down spiral than a minor satellite tagging along. For observers in the southern hemisphere, it stands out to the naked eye, visible as a cloudy patch in the night sky that has been known to humans long before telescopes were invented. Its brightness and structure make it one of the most remarkable examples of a companion galaxy, and one of the most studied as well. Scale and structure. Its estimated stellar mass is around 1/10 that of the Milky Way, which means it's enormous by the standards of satellite galaxies. It also appears to contain a large halo of dark matter, which allows it to hold itself together even as it passes close to the Milky Way. That stability has allowed it to keep an organized structure rather than being torn apart. Astronomers can trace the way its stars form patterns across the sky, with clear evidence of spiral arms and a central bar of stars, much like those seen in galaxies far larger. This is one reason why the LMC occupies such an unusual place in the galaxy family. It seems to straddle the line between being a true independent galaxy and a satellite bound to our own. Active star formation. Star formation is happening at a rapid pace compared to many other nearby galaxies, including our own. One of the most famous star-forming regions in the entire sky, the Tarantula Nebula, sits within its bounds. This nebula is a sprawling glowing cloud of gas and dust, where new stars are being born in great numbers. The brightest and most massive stars known have been found inside it, shining with such power that they illuminate the entire region. Supernovae have also been observed within the LMC, their explosions lighting up its skies. In 1987, the closest supernova visible to Earth in modern times occurred in the LMC, giving astronomers an unparalleled chance to study how such an event unfolds in detail. That single explosion, known as SN 1987A, remains one of the most important astronomical events of the past century. And it happened right inside this remarkable galaxy. Gas reserves and orbital history. Many small galaxies have lost their gas, but the LMC still has large reserves of hydrogen, providing the raw material for stars to keep forming. This supply of gas may be partly due to its size and partly due to its orbit, which has only recently brought it close to the Milky Way. Some studies suggest that the LMC is on its first close pass around our galaxy, meaning it hasn't yet had time to be fully disrupted by the Milky Way's tidal forces. If true, then we're catching the LMC at a special moment in its history, just as it begins to feel the grip of a larger neighbor. For years, astronomers assumed the LMC had been circling the Milky Way for billions of years, completing many orbits. But more recent measurements of its velocity suggest it may be moving too quickly for that to be the case. Instead, it might have only recently fallen into the Milky Way's sphere of influence, perhaps bringing along its own smaller companions. If that's correct, then the LMC is more like an intruder than a long-term partner. A separate galaxy that's only now becoming a satellite. Gravitational influence. The LMC's gravity is strong enough to tug on the Milky Way itself, shifting the motions of stars in our galaxy's disk. Some astronomers believe that the Milky Way's dark matter halo may even be distorted by the pull of the LMC. The interaction between the two galaxies has also left behind a vast trail of gas called the Magellanic Stream. This ribbon of material stretches across much of the sky, stripped from the LMC and the small Magellanic Cloud by gravitational forces. The stream may one day rain down onto the Milky Way, fueling new bursts of star formation in our galaxy. If the Milky Way was smaller, or the LMC farther away, we might classify it differently. The fact that it lies in this gray zone shows how nature resists simple categories. Galaxies, like all cosmic objects, exist on a spectrum. For humans on Earth, the large Magellanic Cloud has long been more than a scientific puzzle. Navigators and storytellers in the southern hemisphere wove it into their traditions. Today, with telescopes and satellites, we can explore its depths in detail, but it still carries that same sense of wonder. It's a galaxy that is both near and foreign. The Small Magellanic Cloud, torn between giants. The Small Magellanic Cloud, SMC, is an unusual companion. It doesn't have the neat spiral arms of a disk galaxy or the smooth glow of an elliptical. Instead, it looks disordered and lopsided, more like a patch of scattered light than a carefully built system. Over time, the picture that has emerged is that the SMC isn't a galaxy living in calm isolation. It's caught in a tug-of-war between two giants, the LMC and the Milky Way. Its strange appearance is a direct result of being pulled in different directions at once. Close cosmic neighbor. The SMC is located about 200,000 light-years away from Earth. That's close enough in cosmic terms to make it one of the nearest galaxies outside the Milky Way. It contains only a few 100 million stars, far fewer than its larger sibling. This means the SMC is a small galaxy even by dwarf standards. Because it's so close, astronomers can watch how its stars, gas, and shape are changing as forces from the outside pull on it. Instead of being a clean sphere or disk, it stretches in an irregular pattern, with regions of dense stars separated by gaps of empty space. One area looks like a main body, while another looks like a detached wing, as if a piece of the galaxy has been stretched away. Tidal distortion. This structure is believed to be the result of tidal forces. The two Magellanic Clouds are close enough that they form a pair, orbiting the Milky Way together. For billions of years, they've likely been circling each other, while slowly spiraling inward toward our galaxy. Their mutual gravity binds them, but it also distorts them. The SMC, being the lighter of the two, is the one most obviously bent out of shape. Astronomers think the wing-like extension of the SMC is the result of a close encounter with the LMC, which stripped away part of its material and left it trailing. Another clue to the SMC's struggles comes from its gas. When telescopes look at the Magellanic Clouds in radio light, they reveal a massive river of gas stretching away from them. This Magellanic Stream arcs across the sky for hundreds of thousands of light-years. It's thought to have been pulled out of the SMC and LMC during their repeated encounters with each other and the Milky Way. The SMC, with its lower mass, has lost more of its gas than the LMC. This is one reason why the SMC looks patchy today. Star formation activity. The tidal pulling has also influenced how stars are born inside the SMC. Normally, star formation in a galaxy depends on the availability of cold gas clouds. In the SMC, astronomers see evidence of starbursts in its recent history. Some regions contain clusters of very young, bright stars, indicating that gravitational stress has sparked new activity. At the same time, other areas appeared depleted, as if the fuel for star formation has already been swept away. This uneven pattern fits well with the picture of a galaxy caught in an ongoing struggle. Because it's nearby, scientists can measure its stars and gas in detail. They can even track how some of its stars are moving through space using precise instruments. These measurements show that the SMC isn't simply drifting quietly around the Milky Way. Instead, it has a complex orbit. The irregular shape could be a sign that it's still adjusting to life under the Milky Way's pull. Future fate astronomers debate whether the SMC and LMC will eventually merge with each other before being absorbed into the Milky Way. If they merge, the combined system may resemble a larger dwarf galaxy, though still far smaller than the Milky Way. If instead, the Milky Way's gravity tears them apart first, the SMC may eventually dissolve, leaving its stars scattered across the sky as streams and clusters. Either way, its current irregular form shows that it's already well on the way to being reshaped. Like its larger sibling, it appears as a fuzzy cloud of light visible to the naked eye on clear nights. Sailors once used it for navigation, and observers noted its unusual hazy appearance centuries before telescopes revealed its true nature. The SMC is a living example of what happens when small systems are caught between giants, reshaped by forces they cannot escape. The Magellanic Bridge and Stream, tidal scars in the sky. The Magellanic Bridge is a structure of stars and gas that physically connects the LMC and SMC, almost like a tether between them. For a long time, the clouds were thought of as two separate neighbors drifting near the Milky Way. But observations in the 20th century revealed that they were bound together, and the gravitational pull between them had drawn material out of the SMC and into the space between the two. When astronomers looked more closely, they saw streams of young blue stars stretching across this gap, showing that star formation had even taken place in this bridge, sparked by the compression of gas as it was torn out and reshaped. The Magellanic Bridge is a snapshot of motion, the material caught in the middle of being traded and stripped during a long, ongoing encounter. The vast stream. Even more striking is the Magellanic Stream. Unlike the bridge, which sits between the clouds, the stream extends far beyond them, wrapping across the sky behind the pair as if they were dragging a comet's tail. This stream is made of hydrogen gas, stretched out over more than 600,000 light years, longer than the Milky Way itself. It's faint and invisible to the naked eye, but radio telescopes tuned to the frequency of neutral hydrogen can detect it clearly. The Magellanic Stream tells the story of repeated tidal encounters between the clouds and the Milky Way. Each time the dwarfs swing around, some of their gas is pulled loose, left trailing behind in space. Over billions of years, this has created a ribbon so vast that it circles much of the southern sky. Gas is the fuel for star formation, and when galaxies lose too much of it, they stop making new stars and slowly fade away. The stream suggests that the Magellanic Clouds cannot keep their material forever. In time, much of what once belonged to them will fall into the Milky Way, feeding its halo and perhaps sparking bursts of new star formation within our own galaxy. Complex structure. A fascinating aspect of these tidal features is that they're not uniform. The bridge and stream show knots, clumps, and filaments, as if the forces pulling on them were not steady, but chaotic. Some parts of the stream appear denser, while others fade into nothing. The reasons for this are still being explored. Part of it comes from the uneven gravity of the Milky Way, which doesn't pull evenly across the clouds. Part may also come from the interaction of the stripped gas with the thin atmosphere of hot plasma that surrounds our galaxy, known as the circumgalactic medium. As the Magellanic gas moves through this halo, it's stretched, twisted, and even eroded, leaving behind a ragged pattern rather than a smooth arc. Cosmic laboratory. In the distant universe, astronomers often see galaxies merging or tearing at each other. But those are usually so far away that only the broadest structures are visible. Here in our cosmic backyard, we can map the stripped gas, almost cloud by cloud, star by star, and use it to test our models of how gravity and tidal forces work over millions of years. The bridge shows us what happens when two dwarf galaxies pass close enough to exchange matter, while the stream shows what happens when those same dwarfs fall into the sphere of a much larger host. Together, they're like a laboratory of cosmic dynamics, visible not with exotic equipment, but with radio dishes and patient mapping. With instruments like the Australia Telescope Compact Array, the Parkes Radio Telescope, and space observatories such as Gaia, the details of the bridge and stream are becoming sharper. By tracking the motions of stars within the bridge, researchers can reconstruct the history of when the clouds last passed closest to one another. By measuring the chemical makeup of the stream, they can determine whether the stripped gas came mostly from the small Magellanic Cloud, the large, or a mix of both. These questions matter because they tell us not only about the fate of the clouds themselves, but also about the long-term flow of matter into the Milky Way. Sagittarius dwarf galaxy, a victim of cannibalism. The Sagittarius dwarf galaxy is a fragile system caught in the grip of the Milky Way's enormous gravity. And unlike the Magellanic Clouds, which still hold together, Sagittarius is already being torn apart. It's a living demonstration of galactic cannibalism. Astronomers first recognized the Sagittarius dwarf in the 1990s, and even then, it was already showing signs of distress. Its stars stretched out in long, faint streams that wrapped around the Milky Way, like a necklace broken apart and scattered across the sky. Instead of being a neat, compact ball of stars like many other dwarfs, Sagittarius was elongated and shredded, caught in a process that has been going on for billions of years. The fact that it was discovered so late shows just how faint it had become. Much of its original mass is no longer bound to the galaxy itself, but has been stolen and spread throughout the Milky Way's halo. Destructive orbit. The story of Sagittarius begins with its orbit. Unlike a quiet companion that circles far away, this dwarf plunges directly through the Milky Way's disk on a path that guarantees repeated encounters. Each pass subjects it to tidal forces. As Sagittarius swings past, the Milky Way's gravity pulls harder on its near side than its far side, slowly prying stars and gas away. With every orbit, it loses more of itself, peeling away, layer by layer, until only a small core remains. This violent process leaves scars that are visible across the night sky. The stellar streams from Sagittarius wrap around the Milky Way like a ribbon wound around a globe. These streams aren't just beautiful, they're scientific treasure troves. They act as test particles, tracing the shape of the Milky Way's gravitational field. By mapping where the stars go, astronomers can infer the unseen distribution of dark matter that gives the Milky Way most of its mass. In this way, the death of Sagittarius provides a gift, a way to study the structure of our own galaxy. Scientific legacy. Some studies suggest that its repeated plunges may have triggered star formation bursts within our galaxy. As it passed through, it may have stirred up clouds of gas, compressing them until they collapsed into new stars. If so, then the legacy of Sagittarius isn't only in the stars it lost, but also in the stars it helped bring to life within the Milky Way. The relationship is parasitic and creative at the same time. Sagittarius isn't the first dwarf galaxy to meet such a fate, and it won't be the last. The Milky Way's halo is littered with remnants of past meals, faint streams of stars that once belonged to other small galaxies or clusters. Each stream tells a story of a past encounter. But Sagittarius is unique because we're watching its destruction happen in real time. It's a rare case where the drama unfolds in the present, giving astronomers a front row seat to galactic cannibalism. What remains of Sagittarius today is a faint core, orbiting about 70,000 light-years from the center of the Milky Way. It's still recognizable as a galaxy, but only barely. Compared to its likely original size, it's a shadow of itself. Its stars have been redistributed across the sky, some now indistinguishable from those born in the Milky Way. Over time, the core will continue to shrink until even that is gone, completely consumed by the larger galaxy it orbits. Broader implications. How many of the Milky Way's stars were stolen rather than born within it? How many ancient dwarfs were swallowed long before we had the tools to trace their remains? And how does this steady diet of smaller companions shape the growth and evolution of galaxies like our own? In Sagittarius, we see one answer unfolding, but the broader picture is that this is how galaxies grow. They consume their neighbors, merging and blending until their histories are inseparable. The Milky Way itself will one day merge with the Andromeda Galaxy, an event on a far grander scale, but built on the same principles at work in Sagittarius's demise. The streams of stars from this small dwarf are the first hints of what happens when two galaxies cannot resist each other's pull. Today's journey comes to an end. But what other cosmic mysteries would you like us to explore next? Share your thoughts in the comments below. And if you enjoyed this deep dive into the dwarf galaxies orbiting our Milky Way, consider subscribing to Stellify Science for more fascinating journeys through the cosmos. Your support helps us continue bringing you the latest discoveries from the universe around us. Until next time, keep looking up.